Hey everyone, it's Mr. Glover here. So the topic today, we're starting a new chapter. We're starting on polynomial functions. So we're going to talk about what polynomial functions are. We will define them. We will spend a bit of time graphing them, taking a look at what the different types of functions look like. And we're going to talk about characteristics and things that you should look for when you're sort of determining what kind of polynomial you've got. So first and foremost, in math, a polynomial is an expression consisting of variables. Polynomials may involve one or more terms, but they have to have an x in there. So you could have something like x, literally just y equals x. You could have something like x plus 3. You could have something like x squared minus x, x cubed minus 2. You could even have something like 4x to the power 5 minus 7x cubed. That's a polynomial. It just has a combination of powers of x. In general, a polynomial function is of the form f of x or y, so I'm going to call it f of x, equals a(n) x to the n plus a(n minus 1) x to the n minus 1 plus a1 x to the 1 plus a0 x to the 0. So this looks kind of daunting and this looks very general. But what this means is a polynomial function has a combination of powers of x, and I've written those as descending powers. We start at n, some given number, and then we've got a power less than n, power less than that, and a power less than that, all the way until x is to the power 0, which makes it 1. And then there can be coefficients or numbers being multiplied by your powers of x. So n is going to represent a whole number. X is going to represent a variable. And an through to a0 are what are called coefficients. So these are whole number coefficients. So let's go through some examples, some things that are and aren't polynomials. Something like y equals 4x plus 2. That is a polynomial, that's a linear function. You could have something like y equals 2x squared minus 1. That's a polynomial, that's what you call a quadratic function. You could even have something like y equals 4x to the power 4 minus 3x squared. That is a polynomial, that's called a quartic function. And you can also have things that aren't polynomials. Something like y equals the square root of x. That's not a polynomial because your powers of x are not whole numbers. Something like y equals the absolute value of x. Again, it's not a polynomial. You could have something like y equals 3 divided by x. And because x is in your denominator, it's not a polynomial. The degree of a polynomial refers to the highest power of x. So for example, x to the 4th plus 3x squared minus 1, the highest power of x is 4, so the degree is 4, and we call this a degree 4 polynomial. If we had something like x squared plus 3, well, that's degree 2. So the degree is one of those things to look for. It's one of the defining characteristics of a polynomial. It's going to tell us what the shape of the function looks like. Some other things to look for. A coefficient. A coefficient is a number which is multiplied by a variable in an algebraic expression. The leading coefficient of a polynomial is the coefficient of the highest power of x. So for example, if we go up here, 4x to the power 4, 4 is your leading coefficient. In this case, we need to look for our highest power of x, and it's not always the first term. For this question, our highest power of x is right here. So for this question, our leading coefficient is minus 3. Minus 3 is the leading coefficient. You may have heard of quadratic functions or linear functions. So you may have heard linear functions or quadratic functions, but there are many possible polynomial functions. These functions have common characteristics, and they relate to the degree of the polynomial, as well as the leading coefficient. So some common characteristics. One common characteristic is going to be the x-intercepts. Another is going to be the y-intercepts. The orientation. And when I say orientation, I'm talking about whether it opens up or whether it opens down. The shape of the function, the domain, as well as the range. And if you don't remember, the domain represents all x values, while the range represents all y values. We may also consider the end behavior of the polynomial. So I'm going to draw two different graphs for you. One of them will have similar end behavior and one will not. So let's take a look at one that doesn't have similar end behavior. Let's take a look at a function that looks something like this. This has what I would call opposite end behavior versus something else like this. This has the same or similar end behavior. And what I'm talking about is the directions that the function moves off in. This function, one is pointing up, one is pointing down. So they will continue going in opposite directions forever. This function, one is pointing up and the other is pointing up. So they will always point in the same direction. We can use our graphing calculators to sketch the graphs of polynomial functions to get a sense of what each type of function should look like. So we're going to use technology to graph the following functions: x squared, x cubed, x to the 4, and x to the 5. So let's go into Desmos, let's graph these, and then we can draw a quick little sketch of what they look like. So switch over to Desmos. So we'll start out with just y equals x. This is a function you've probably seen before, and it's a straight line. This is a degree 1 function. Okay, let's change this to x squared. That's what x squared looks like. This is called a parabola. And that's the name of this kind of U shape. Take a look at x cubed. There's x cubed. Let's take a look at, by the way, this is called a cubic function. Let's take a look at x to the power 4, a degree 4 polynomial. Looks like this. And lastly, let's take a look at degree 5. It looks like this. So you might be noticing a bit of a pattern. And when we draw them side by side, I think the pattern will become more clear. Okay, I'm going to go back to our notes and draw a sketch. I'm going to try to exaggerate some of the characteristics though. So y equals x. Actually, let's just draw our axes first. Oops. All right, so y equals x. As we saw, y equals x is basically just a straight line, and it's either going to point up like this or it'll point down. That's a degree 1. X squared looks something like this. That's a degree 2. X cubed looks something like this, and I'm going to exaggerate the zeros. It's going to look like that. That's degree 3. X to the power 4 is going to look something like this. That's called a degree 4. That's called a quartic function. And then x to the power 5 is going to look something like this. That's degree 5, and that's what you call a quintic function. So you might be noticing some patterns here. I'm hoping you're noticing some patterns here. All of the odd degrees seem to have a similar end behavior. Degree 1, degree 3, and degree 5 all have opposite end behavior. However, the even functions, so x squared or x to the power 4, or I suppose x to the 6 if we were to go there, they're going to have similar end behavior. That's one of the characteristics you want to look for. All right, you may find some patterns if we consider the progression of polynomials. So this is where we're going to write out some of these characteristics. First one's degree 0. This is a constant function. The end behavior is, it's literally one number. It's always y equals 3. I suppose you could call it similar end behavior. The number of x-intercepts is 0, unless you have a function on the line y equals 0. And then I don't know whether you'd call that infinitely many zeros or 1, or I don't know. But for now, we're going to say no x-intercepts. Let's take a look at degree 1. These are called linear functions. They are going to have opposite end behavior. And you are going to have one x-intercept. You will always have one x-intercept because it has to cross when one points down and one end points up. Let's take a look at degree 2. These are called quadratic functions. So this function has the same end behavior. They will either both point up or both point down. And then the number of x-intercepts. You can have 2, but you can also have 1 or 0. So 2, 1, or 0. And that depends on the orientation of the function. For example, I could give you, well, you've seen one that looks like 2. You've seen one that looks like 1. I don't think I have anywhere to write this. You could have a function that never actually crosses the x-axis and simply looks like this. So you don't always have to have an x-intercept for these kind of functions. Degree 3, we have opposite end behavior. And then the number of x-intercepts can be 1, 2, or 3. You have to have at least 1 because of the opposite end behavior, but this second and third one depend on the function. So you can have 3, 2, or 1. This is called a cubic function. Degree 4, those are called quartic functions. Quartic functions have the same end behavior, and they can have up to 1, 2, 3, or 4 x-intercepts. They don't have to have an x-intercept. They're similar to a quadratic, where you could have one that never touches the x-axis, but you can have up to 4. So you can have 4, 3, 2, 1, or 0. And lastly, degree 5s. These are called quintic functions. They have opposite end behavior. You must have at least 1 x-intercept, but you can have up to 5. You can have 1, 2, 3, 4, 5. So we've now figured out 3 different characteristics. We've figured out the end behavior. We've figured out the number of x-intercepts, and we've also figured out what the general shape of the function is going to look like based on the graph. It's going to be different. You'll have more dramatic or less dramatic slopes depending on the actual function, but they have a basic shape. Quadratic function is going to be a parabola of some sort. It might be flattened out, it might be really steep, but it's going to look like this. A linear function will look like this. It might be flat, it might be steep, but it's got that shape. Quartic functions have 1, 2, 3 changes in directions. Cubic functions have 1, 2 changes in directions. Quintic functions have 1, 2, 3, 4 changes in directions. All right, notice that the end behavior is determined by the sign of the leading coefficient. You might not have noticed this yet, what the number that you have in front of your highest power of x dictates whether the function opens up or opens down. And I'm going to demonstrate this in Desmos right now. For example, let's do a quadratic because actually no, let's do a quartic. Let's do a quartic. So this is just the basic quartic function. In this case, you have a leading coefficient of 1. That's positive, so it opens up. If we switch this to like -1, it opens down and it flips upside down. And it doesn't have to be 1. It could be -5, could be -0.5. That negative in front of your leading coefficient dictates whether or not it opens up or down. And it's always going to do that. I can add more terms. I can add like plus 3x cubed. Now we've got a quartic function that looks like this. However, it still opens down because the leading coefficient is the dominant term. That's the one that's going to dictate the orientation. You may also notice that the y-intercept is simply the constant term. This isn't something that I pointed out, but it's something that you might have noticed. If you look at the constant, the number that's at the very end of your function that doesn't have an x attached, that's your y-intercept. And it makes sense. If you had something like y equals x squared plus 3, as soon as x equals 0, that locks you into the y, or the line x equals 0. That's the y-axis. X equals 0 means that your x term is gone. It's 0. All that's left is your constant. And so if I was to go and graph this, if I go back to Desmos, let's just tack on a number. Let's tack on plus 7. Now I have to have a y-intercept of 7. And last but not least, the number of turning points are what are called local maxima, minima, may be 1 less than a degree. And that comes from these pictures. This is degree 1, you have 0 changes in direction. This is degree 2, you have 1 change in direction. This is degree 3, you have 2 changes in direction. This is degree 4, you have 1, 2, 3 changes in direction. And this is degree 5, we have 1, 2, 3, 4 changes in direction. And sorry, I should probably be careful. They're not always just local. Let's just call them maxima or minima, because some of them can be local and some can be absolute. The difference is that one of them, absolute max, is like the highest point, or an absolute min is the lowest point, while local max or min refers to like a min or a max somewhere in the graph that's not necessarily the lowest point. Like this is a local min, this is a local max, but you don't really need to worry about that. So let's put this to the test. We've got 4 functions and 4 pictures, and we need to figure out which picture matches which function. So I'm going to have to kind of rewrite these because for whatever reason, when I turn this into a PDF, it kind of botched my function. So this is minus 1x to the power 4 plus 10x squared plus 5x minus 4. So this one is a quartic function. This is minus 2x to the power 5 plus 5x cubed minus x. This is x cubed plus x squared minus 5x plus 3. And this one is x to the power 4 plus 4x cubed minus x squared minus 16x minus 12. Okay, so let's use what we know to figure out which functions are which. Right off the bat, I know I have 2 quartic functions. I have x to the 4 and x to the 4. So 2 of them should have that general shape. So let's not start with those. Let's eliminate the other ones first. I know what a cubic function looks like. It has opposite end behavior and it has up to 2 changes in direction, okay? So let's start with f of x. Now I know it's not gonna be b and d because these have the same end behavior, so it's a or c. A has 2 changes in direction while C has 1, 2, 3, 4. C can't be cubic because it has too many changes in direction. So A has to be f of x. So we've knocked out f of x. All right, so then let's look at C. I know C is not quartic because it has opposite end behavior. It has to have an odd power of x. And it has 1, 2, 3, 4 changes in direction. Since the changes in direction must be 1, or can be up to 1 less than the degree, I know this has to be at least degree 5. And I have 1 degree 5. Another thing that you can use as evidence is we have a negative leading coefficient. So my function should start at the top and work its way down, rather than starting at the bottom and working its way up. That's what this function does. It starts at the top, works its way down. So I know that this function must be p of x, and I know that p of x must be c. So now I have to decide which of these is g and which of these is h. They're both quartic functions. I know that because they have the same end behavior and they have 1, 2, 3 changes in direction. But I don't know which one's which. So I need to use some other clues that I know, or pieces of evidence that I can use. I mean, we could use the constants, I suppose. H of x should have a y-intercept of -12, and g of x should have a y-intercept of -4. But a better way to do it, because I'm estimating here, is to just look at the leading coefficient. G of x is a negative, while h of x is a positive. So that means g of x should open down and h of x should open up. That means b is h of x, or h of x is b, while d has to be g of x because it opens down. So g of x is d. So I didn't need a graphing calculator to figure out any of these because all of them have specific characteristics that I need to look for. Now, I don't expect you to take this function and know that it looks like this, but I know that if I give you this picture, you can use what you know to work backwards and figure out that this is a quartic function. Because odd degree polynomials have opposite end behavior, we're guaranteed the existence of at least one x-intercept. Because even degree polynomials have the same end behavior, we're guaranteed the existence of a maximum or a minimum. And that comes back to the fact that both ends are either pointing up or both ends are pointing down. If I have let's not do a quadratic, let's do a quartic. Let's do something like this. This point is what you call the absolute max because this point is literally the highest point. It's the maximum on the function. Compare that to, let's do a quadratic. If you've got a quadratic that looks like this, this point is what you call an absolute min because that's literally the lowest point. So that's where I want to stop today. We've kind of taken a look through some different functions. We've sketched some, we've looked at characteristics. The characteristics you need to know about are the leading coefficient affecting the orientation, the constant affecting the y-intercept, and the degree of the function dictating the general shape. Linear, quadratic, cubic, quartic, quintic functions all have different shapes. And then we have some other little pieces of information that we can use to kind of piece together the functions. So for now, I want you to try some questions out of your textbook, page 392, 1 to 7. That's going to be your homework for today. I think I'll end the video now. So if anything comes up in the next day or so, just send me an email and I'll see if I can get back to you and answer your questions. If not, I'll see you all either in class or in our meeting on Wednesday. So take care. Have a good rest of the day. Bye for now.